theorems and basic methods by which you can find out these currents. Okay, this I1, I2. Let us say some again here the resistance values are given, and there is a current source. Again, this is a independent current source. Circle is there. Inside the circle there is an arrow. Circle means it is a independent. If it's a diamond shaped, then it will be a dependent, that we discussed yesterday. So it is a independent current source. Value is also given 13.7. Then what are these I1, I2, I3, I4, I5, I6? That means the current in different branches, and also the node voltages VA, VB, VC, all these things. What are these values? To find this out, this looks like a complex circuit. It can be more complex, more different elements. We will see how they can be incorporated, and things will become complex. Then we need a structured method to find out these values of different these unknown variables. Okay, for that we will start with the most basic one, that is the KCL, KVL. Okay, but again, to find out current, what is important is direction of the current. Magnitude is important, like unilateral, bilateral. Magnitude is important, but direction is also important. So first, we will use a convention. This convention will be used throughout this subject. Okay, you can use your own convention, but beware that whatever convention you use it throughout solving a particular problem. If you change the convention in between solution of a particular problem, it will be wrong. Okay, so whatever convention you follow, just or you already know some convention from your previous learnings, you can also use that. So I will be using this or whatever the notes you will get, lecture slides, in that this convention will be used. Okay, here the current entering a specific node, again node, interconnection of two or more elements, this is a node. Okay, so when a current is entering a particular node, that is taken as negative current, the sign is negative. And if the current is leaving a particular node, that means it is positive, it is taken as positive. Vice versa is also fine, but again, whatever convention you will be following, you have to follow throughout the solution of a particular problem. Now let us see I1. If you see this node, okay, I1 is moving like this. Okay, I1 is moving like this. That means it is going outside, or it is going out from the node. Okay, away from the node. So it is taken as positive. Again, I2 is going out or going away from this particular node. So I2 is also taken positive. I3, you can see it is going into the node. So it can be taken as negative. Okay, if it is going inside the node, it is negative. It is going out of the node, it is positive. So this is the convention we'll be using throughout our this. So again, then Kirchhoff's current law. So you can see this black dot, that is the node, and there are various branches. Okay, various branches that are ending at that particular node, and you can see some current are denoted I1, I2, I3, I4. Okay, uh, so node. What is a node? Node is not a like a device or some. If there is a capacitor, it can store it can store charges. Okay, it can store some energy, but node doesn't have that capability. Node, in particular node, it is junction point. It cannot store any charges. Okay, so whatever current, by current I mean charges, q by t, q dq by dt, that is the current. So whatever charges is entering the node, that same amount of charge will be leaving. Conservation of charge, nothing is getting destroyed here, no charges is being added here, because node doesn't have any capability. This is like a intersection point. So if you take the sum of the all the currents that are coming into a particular node, that will be equal to all the currents that are going out of that particular node, because again, due to the conservation of charge, and this any node do not have any energy storage capability or charge storage capability. Okay, so we will use the same convention. That means I1 is entering the node. If it is entering, we will consider it as negative. I2 is entering the node. See arrow on this side, that is entering the node. So again, this is negative. I3 is going away, so it is positive. If you have any doubt, please unmute yourself and you can always ask, write in the chat anything. I4, okay, I4 is going out, so positive. Now what I have told, the conservation of charge storage, that means whatever current is entering the node, that means I1 plus I2, that should be equal to I3 plus okay. So see, 3 is going out, 3 is going out of this node. So I have already told, if it is going out, it is positive current. If it is going in, it is a negative current. So plus 3, you can see it is plus 3. Okay, 2 ampere current is going into that node, so minus 2. 7 ampere current is going into that node, so minus 7. I1 is going into this node, so we have taken at it as minus I1. We don't know what is I1. So in this, there is a single unknown variable, and you can find out what is the value of I1. I1 is again 9 minus 9 plus 3. Okay, so 6 minus 6. Okay, this I1 is also negative, so I1 you can take on this side. So I1 will be equal to minus 6 ampere. So I1 you have found using KCL. You have applied the KCL on this particular node and you have found out what is I1. Similarly, here, when you apply KCL, Kirchhoff's current law in this node, so what you can see, I2 is flowing out. I2 is flowing out. So plus I2. You can see plus I2. I1 is flowing out. So plus I1. 1 ampere current is flowing out. That means plus 1. And 4 ampere current is going in. So minus 4. And the net sum will be equal to 0. So I1 we have already found minus 6. So minus 6 minus 4 is minus 10 and plus 1 is minus 9. So I2 is positive here. Minus 9 you are taking on the other side. So I2 will be equal to 9 ampere. Okay. So these are the two simple examples of KCL. Now KCL, means as such, KCL only solving problem using KCL. As such, solving problems only using KCL is, means you cannot find those simple problems. Okay, so KCL will be part, more theorems you have to apply. Okay, so this basic with this basic understanding of KCL, we will go into some advanced topic. Okay, like nodal analysis, so mesh analysis. Those things we will do next. Okay, so this is the first basic theorem, that is KCL. If you have any doubt in KCL, please let me know. Next is Kirchhoff's voltage law. Okay, to apply KCL, you only need a node. Okay, to apply voltage law, you need some kind of a loop, not a mesh. You need a loop. Okay, so what it is telling, what Kirchhoff's voltage law is telling that the algebraic sum of all the voltages around any closed path, that is a loop. Okay, not a mesh. Oh, it is also applicable in mesh, but we are talking about loop. We are not going into the specifics that mesh is a loop with no other loop inside it. No, it is only a loop. There can be other loops inside it. So you take any closed path. If you take the algebraic sum of all the voltages, by voltages means there can be some kind of a source, there can be some kind of a sink. By sink I mean if there is a resistance that is absorbing some kind of a power. Okay, so what will be the voltage across that resistance? There will be a voltage drop across the resistance. If the resistance is drawing power from the voltage source, then definitely there will be a voltage drop. Okay, there will be a voltage drop across a capacitor also. So that we'll understand. But now we are only seeing a circuit, the circuit that you are seeing here. Okay, and there are some elements. We don't know what is this element. It may be any kind, resistance or anything. It's circular, that means it will be a voltage source. Okay, and say V1 and V2 is given, so it will be a voltage source. And this red element, it can be anything. It can be resistance, it can be other kind of elements, but it is just an element here. and you are seeing that there are various voltages that are given, V1 across this green element, V2 across this blue element, V3 across this red element, and their polarities are given, like which side is positive, which side is negative, that is also given. Okay, nodes are also mentioned, A, B, C. These are the three nodes, interconnection of two elements here. So KVL is based on conservation of energy. Okay, that means whatever, like it's a closed path. Okay, no outside energy is coming into it. So whatever energy one of the element is giving out, that energy will only be absorbed by the other elements. Okay, the total energy that is given out and the total energy that is absorbed, that should remain same inside this closed path. Okay, so that is the conservation of energy. KCL, conservation of charge. That means the node KCL was conservation of charge, because the node cannot store any charge. So whatever charges were coming in, that should be going out. So here, whatever energy in KVL, whatever energy is being delivered by a particular element, the same energy will be absorbed by the elements that are there to absorb those energy. So that is the conservation of energy. So if you take the sum across a particular, in a particular loop, that will be equal to 0. Okay, we are talking about energy. Okay, and let us see how KVL looks like and how it is related to energy. That also we will see the same circuit here. So how you have to apply KVL? The first thing you have to do, you have to denote this plus minus sign. Okay, it can be like you are wrong, that okay, let us say you have given the plus sign here, you are given the minus sign here, but after solving the problem you will see that okay, it is the opposite. Just for applying, you need some kind of a sign convention. So let us consider this plus minus, minus plus this. There is a way that we will discuss, but even let us say you don't know what will be the voltage across a particular, means which side will be positive and negative. You just give some kind of a convention, okay, plus minus, and the final answer will give you whether that whatever you have considered is correct or not. Okay, so first you have to give this plus minus sign. Okay, then what you have to do, you have to go in clockwise direction. In clockwise direction, take this element first, then this element, then this element. In this way you have to go in clockwise direction. So moving around the closed path in a clockwise direction and writing down the voltages of each element that you are meeting. Okay, you have to see that. Okay, let us say we are going in clockwise direction. We have started from this green element. Okay, that means if we go in clockwise direction, which is the first sign that you are meeting first? You are seeing the negative sign first. Okay, you are seeing the, if you go in the clockwise direction, you are seeing the negative side first. So minus V1. So minus V1. Again, clockwise direction, next element will be this blue. So here you are seeing, you are meeting the positive sign first. So plus V2. Here in the negative element, in the red element, you are encountering the negative sign first. So minus of V3. The sum will be equal to 0. Then you can definitely ask me that, so we are, KVL denotes that, okay, KVL denotes, you can ask me that, you said that KVL comes from conservation of energy, but you are writing that minus V1 plus V2 minus V3 is equal to 0. Whether this sign is correct or not, it is just given that if you want to find Vx, then this should be the sign. Okay, if you want to find Vx, then this should be the sign. Based on this, we have to find what is the Vx value. We don't know how much current is flowing, Ix is unknown. But since it's a series, okay, since it is series, you know that the current flowing through all the elements will be same. In parallel the current like divides into multiple branches, but in series the same current flows through all the elements. Now by voltage drop, okay, what will the voltage across this green voltage source? That is 5 volt, and plus will be on this side, minus will be on this side. Again, what will the voltage across this blue? It will be 7 volt, minus on this side, plus on this side. Okay, but what will be the voltage drop across the resistance? By voltage drop I mean using Ohm's law, you know V equal to IR. R is given to you, Vx you have to find, that is voltage across the resistance. I you don't know, that's why we are considering it as Ix, and R you already know, it is 100 R. Okay, now let us move in clockwise direction. Let us first start with this green. So if you move in clockwise direction, then what is the sign you are encountering first? Minus sign. So minus 5 volt. If you see this, minus 5 volt, minus 5 volt. Then what is the sign you are encountering first? Minus 7 volt, minus 7 volt. Then if you see what convention is given, plus is given here, minus is given here. If you move in clockwise direction, what you are encountering first? Plus sign. So plus Vx, the sum would be equal to 0. From this you can find out, okay, what is Vx? That is equal to minus 5 minus 7, that is minus 12. Minus 12 you are bringing on the right hand side, so Vx is equal to 12 volt. Okay, now if you want to find current, what will be the Ix? Then using Ohm's law, Vx you have already found here, that is 12 volt. Ix multiplied by 100, so Ix will be equal to 12 by 100, so 120 milliampere. So this is a simple example of KVL. If you have any doubt, please write in the chat. If you have any doubt, you can also raise those doubts. Okay. Yes, I've already told you, you can move in anti-clockwise direction, no issue. But then throughout your solution of a particular problem, you have to use the same convention. Otherwise, it will be wrong. If you are using anti-clockwise, use anti-clockwise. No problem. It will, all the negative and positive, whatever you are doing, that will rearrange itself. In that way, this has been made. Okay, so you can move in anti-clockwise direction. So some application of this. One is voltage division. One is voltage division. Very important. Voltage division and current division. These two are very important. Okay. It is not like you only you will be using voltage division. Those cases will not come. There will be a complex problem. There you have to use voltage division. Okay. So these are all the tools and techniques through which you can solve complex circuits. Okay, these will not be used standalone. You can use standalone thing, but rarely, like in complex problems, you have to use it as a part, okay, of a bigger problem. So you can see here what is happening, that there is like two terminals, plus and minus V. So you are applying some voltage here to some battery or something, and in between these two terminals there are three resistances. Okay, some current I is flowing. So this is R1, this is R2, this is R3. Okay, so why it is used? to lower down the voltage. To lower down the voltage, let us say you have a 250 volt supply and you are using a appliance which cannot withstand that much amount of voltage. You have to lower it down. So you can do this using this voltage divider, voltage division. Okay, but it is not a good way of doing that, because you'll be losing energy. You'll be losing. Okay, let us say your appliance is R1. Okay, the load, that is, let us say it is a small load. Okay, you are charging your mobile, so the mobile is the load, so it cannot take that much amount of voltage. Okay, what you do, this is your load R1, but you are also adding R2 and R3 to lower down the voltage, across your mobile charger. Okay, to lower down the voltage across the mobile charger. But what is happening? Okay, your mobile will get charged with a certain amount of voltage, that is okay, but here you are adding some resistances. That means power is being dissipated here, and that is of no use. You are using only to lower down the voltage, so it is not a correct way of doing that. It is lowering down the voltage. It is a like very basic method of doing. Okay, so what is the voltage across a particular resistance R1? So first you have to find out current. What is current? I. You are applying some voltage across these three resistances. These three resistances are in series. So series resistance are added. So the equivalent Req will be added. R1 plus R2 plus R3. Okay. So what is the current flowing? That is, current will be equal to the voltage divided by Req. And Req we already know. It will be V divided by R1 plus R2 plus R3. So what will be the voltage across R1? The current that is flowing, sorry, same current will be flowing I. So there is no need for taking I1, because the series, through a series connected element, same current will flow. So through all R1, R2, R3, the same current I will flow, and I you have already found, that is the voltage you are applying divided by R1 plus R2 plus R3. Okay, then what will be the voltage across R1? That is nothing but you are applying the same, your Ohm's law, V equal to IR. You are trying to find what is V1, the voltage across this, element. So V1 will be equal to whatever the current is flowing through the element, the same current I will be flowing, multiplied by the resistance R1. So I will be, you can V divided by R1 plus R2 plus R3, and in multiplication this R1 will be there. So this will be the, this is the basic voltage division. It is applicable for n number of elements. Okay, it is applicable for n number of elements. So again, this thing you have to solve problem using this. This thing will come again in a more advanced subject, that is instrumentation engineering. In instrumentation engineering, there is small measuring instruments. Okay, if you have worked with, when you will come to lab, you will see that multimeter and everything are there. They have some range. Okay, beyond that range, they cannot measure current or voltage. Okay, so how you can use the same voltage ammeter or voltmeter to measure higher amount of voltage and current? For that you require this concept, you require the concept of voltage division, you require the concept of current division. So this will come later again in your third year or sixth semester. This is voltage division. Okay, if you have any doubt, please let me know. Voltage division, current division. Okay, again, current division means we have to apply the concept of some related concept of KCL. Okay, let us consider this one. Let us say some, again, similar kind of a circuit. Now it is being divided into two branches. Some current I was flowing, and it is like R1, it is like R2. You're applying some voltage V. Now what will happen? In earlier case, the whole voltage V, that was getting divided into three parts: V1 across R1, V2 across R2, V3 across R3. Okay, voltage was getting divided, current was same. Now here the resistances are connected in parallel. That means the current that was flowing through here, that will get divided into two parts, again using KCL. Whatever current is entering, the same current will be getting divided into two parts. That will be definitely I1 will be equal to I will be equal to I1 plus I2, or I1 is entering, so it will be minus I, and I1, sorry, I is entering, so it will be minus I1 is leaving, that means it will be plus I1. I2 is leaving from this node, I am considering this node, so I2 will be leaving, so it will be plus I2. The net sum will be equal to 0, so I will be equal to I1 plus I2 using KCL you are getting. Okay. Now, what will be the values of I1 and I2? That is our main focus here. Okay. So we have already got this. So what will be the net current flowing? What will be the net current flowing? So here there is no element. This is V. This is the voltage you are applying across this terminal. Okay, this terminal, between these two terminals there is no element, so there will be no voltage drop. That means V that you are applying here, the same positive V will be applied here. Okay, and this is ground or 0 volt. Okay, so you are applying V across R1, you are applying V across R2. Then again using Ohm's law is V is equal to IR. Here you know what is the value of V. You are applying this plus V across R1. So V you have already know. I you don't know. I1 you don't know. And what is the resistance? This resistance is R1. So from this you can find out I1 is V divided by R1. Similarly, I2 will be V divided by R2. V divided by R2. So from KCL, we have understood that I is equal to I1 plus I2. Okay, I1 you know V divided by R1, I2 is known you know V divided by R2. Okay, this you already know. Then how this current is getting divided? That means how much portion of how much portion, what fraction of I is going to I1? What fraction of I is going to I2? The sum will be equal to I1 and I2, the sum will be equal to I. But what fraction of I is going to I1? What fraction of I is going to I2? For that, what we can find I1 divided by I. Then you can take the, okay, multiplied by 100 in percentage terms. Okay, 50% of the current is going to I1, 50% of the current is going to I2. In that way, you will get some idea. That's why I1 by I2 you are doing. What is I? So what is I1 in the numerator? It will be V divided by R1. What will be I? We have already found out. V divided by R1 plus V divided by R2. This V you can take common. So this V in the denominator you can take common. So this V and this V will get cancelled. So you will get 1 by R1 divided by 1 by R1 plus 1 by R2. Okay. So if you further simplify this, okay, so I1 by I, you are getting 1 by R1 here, 1 by R1 plus 1 by R2. Okay, 1 by R1, R1, R2 divided by R1 plus R2. So this will get cancelled. It will be R2 divided by R1 plus R2. So I1 will be equal to R2 divided by R1 plus R2. Similar way, if you find what is the value of I2, you will get it R1 divided by R1 plus R2. So what to conclude? So definitely you will not be doing all these steps. When you are applying this current division in a complex circuit, you cannot just do all the steps and everything. You need to understand that. Let us now first see the original circuit. The original circuit was, there was these two terminals across which you are applying voltage V. You are applying voltage V, and there are two like this. Okay, through here I1 was flowing, through here I2 was flowing, here I. So how you will find I1? What percentage? So definitely it will be some fraction of I. It will be some fraction of I. What fraction? In the numerator it will be, let us see, this is R1, this is R2. Okay. If you are trying to find I1, then in the numerator you have to find what you have to write what is the resistance in the other branch. You are trying to find R1. Sorry, I1. In I1, that means I1 will be flowing through R1. Okay. So while finding I1, you have to write what is the resistance in the other branch, that is R2. And in the denominator, it will be sum of these two resistances, R1 plus R2. Similarly, while finding I2, you have to, in the numerator, you have to write the resistance in the other branch. That means R1 divided by R1 plus R2. If you go to three elements, if you go to three resistances that are connected in series, in the same way you can find this out. It is a similar concept. That means there are three resistances, R1, R2, R3, R3, and this is I. This is I1, this is I2, this is I3. Okay, so I1 will be, it will be some fraction of I. But what fraction? Now, except R1, there are two other resistances. So you have to take the multiplication of the other two resistance, R2, R3, divided by all possible combination. That is R1 multiplied by R2, R1 multiplied by R3, plus R2 multiplied by R3. Okay. In this way, you will be using current division. You can derive it using the same concept that I have used previously. You can derive this thing, but in a complex problem you cannot derive and conclude. You have to use whatever your understanding is, and you have to apply directly here in whatever in complex problem that you'll be able to, you are solving. Okay? This is voltage division, current division. Next, star delta we will do when we solve problems. We will do this thing. We are not doing, we are dealing with this here when we solve problems. Next comes the mesh analysis. Now using KCL and KVL, we will be doing two things. One is mesh analysis and the other is nodal analysis. If you know at least these two things, you can solve any kind of circuit. The next theorems that we learn, that will make your job easy. But even if you know mesh analysis and nodal analysis, and which is based on KCL and KVL, you should be able to solve any kind of circuit. Okay. So mesh analysis means, what is mesh analysis? Okay. So if this kind of a circuit is given to you, and you are asked to find, okay, how much current is flowing through this loop or this mesh, how much current is flowing through here, or what is the current flowing through R2. This kind of questions where you have to find out the current that is flowing through a particular loop or a mesh, then you have to use this mesh analysis. It is based on the concept of KVL. It is based on the, so loop is there, you have to use this KVL across this mesh. Okay, again you have to use this KVL across this mesh. But the important thing is here is, it is mesh analysis. It is not loop analysis. That means you have to identify those loops within which there are no other loops. That means you have to identify how many number of meshes are there. For that, I will, just by seeing also you can identify, but I will give you a formula for finding that. This formula, number of mesh current, or how many number of meshes are there. Mesh analysis means in a particular mesh how much current is flowing, that you are finding here. Okay, so to find how much current is flowing through a mesh, you have to identify the each and every unique mesh. Otherwise you won't be able to find those currents. So first you have to identify each and every mesh. So what is the formula? You have to find the number of branches, number of mesh. How many number of mesh are there in a circuit? Number of branches minus number of nodes plus 1. Okay, see whether this current, whether this formula works or not. First find out how many number of branches. So for this circuit that I am showing here, how many number of branches here? Write down in the chat. Branch is a path between two nodes. You have to first find out how many number of branches minus how many number of nodes plus 1. So first find out how many number of branches are there, write in the chat. Okay, write in the chat. So Rajveer is saying 3, Asutosh is saying 4. I am talking about branch. How many number of branch? Clearly write. Node this many number, branch this many number. Arin is saying 3, Mayank 3. Branch 3. So let us first find out what are the nodes. Nodes, again, go to the basic definition. Node is an interconnection of at least 2 or more. So this is a element. This is a active element. B1 battery. This is a resistance. These are being interconnected here. So definitely this is a node. Am I clear? Two interconnection of two elements. Definitely this is a node. First node. Again, this is an interconnection of this element, and this element. This is an interconnection of R1, R2, and R3. So definitely this is a node. So this is a second node. Again, this is an interconnection of B2 and R3. So this is a node. Third node. Again, see this is an interconnection of B1, R2, and B2. Definitely it is a node. So how many number? 1, 2, 3, 4. So 4 number of nodes are there. What is the branch? Path between two nodes. So if this is a node and this is a node, you are seeing this is a path. So this is branch 1. This is a node. This is a node. So this is a path between these two branch nodes. So this is a branch 2. Again, path between this node and this node. So this is branch 3. Path between this node and this node, branch 4. So path between this node and this node, so branch 5. 1, 2, 3, 4, 5. So there are 5 branches. There are 5 branches and 4 nodes. Let me know, is it clear or not? Yes, 5 branches, 2 nodes. Sorry, 5 branches, 4 nodes. So if you apply the formula now, number of branches is 5, number of nodes is 4. So 5 minus 4, it is 1, and you are adding 1 later. So 1 plus 1, 2. And so this formula will give you, okay, there are 2 mesh. And by just looking into the circuit also, basic concept that our mesh is a loop which do not have any loop inside it. So this, if you consider this loop, it does not contain any other loop inside it. If you contain this loop, it doesn't contain any other loop inside it. So this is mesh 1, this is mesh 2, and your formula is also giving 2 mesh. So this is mesh 1, this is mesh 2. You cannot consider this as a mesh because there is a loop. There is a loop inside this outer loop. So definitely the outer loop, it is not a mesh. So formula is also giving you 2 mesh. You are also seeing, okay, there are 2 mesh here. I will start it tomorrow. I will again continue here till KCL, KVL. I will give you the slides today, and whatever recordings I have also I will upload in classroom. So classroom link. Those who have not joined, please join the classroom. Okay. Again, I will give you the classroom link. 17